The increasing use of agricultural drones has had an impressive impact on today's society. Human labor, labor costs, and manufacturing costs have the ability to dramatically decrease by the continuing use of these robots. For example, picking strawberries is very labor-intensive, but with the assistance of a drone, 2/3 of the strawberries can be picked overnight while farmers are sleeping, leaving the farmers to only pick what the drone couldn't reach. Drones such as those similar to Japan's BerryBot are reliable for harvesting on the ground, however they are unable to reach high places. For example, these drones would be unable to pick berries from trees. This problem allows us to introduce our solution. We were tasked with developing a mechanism that could attach to a quadcopter in order to pick berries that are too high for land drones to reach. Although it seems that replacing farmers with drones would have a negative impact on employment rates, it actually has the opposite effect. A marketing research firm known as Metro Martech conducted a study and concluded that the production and use of about 1 million industrial robots have been responsible for the creation of about 3 million jobs. Continuing the use of these drones over the next several years is predicted to be the source of another 1 million high-quality jobs. Once we established the need, gathered customer and engineering requirements, and benchmarked existing designs, we generated several concepts for different prototypes. We narrowed our ideas down to 2 designs, a structure with a fork-like claw, and our current design which involves guiding arms with scissors at the vertex. We decided to go with our current design because we thought it would be more accurate and efficient. While our design can only clip 1 berry at a time, it ensures that all berries, not only loose ones, will be harvested, and it will also prevent bruising and smashing that could happen with the use of a claw. We chose to use rapid prototyping because of the lightweight nature of the 3D printing plastic. It was also much more sturdy and efficient than welding other materials together. We designed the attachments in AutoCAD so that we were able to virtually attach all of the pieces before assembling the physical copy. We initially chose the servo motor to be responsible for the opening and closing of the scissors. The rotating part of the servo motor was placed inside of the scissors. As it rotated, it would open and close. However, the servo did not work out as expected. The rotating part was not long enough to open the scissors completely, and it did not rotate fast enough or with enough power to give the scissors enough force to cut anything. This led us to use a solenoid motor instead. We made the solenoid work with the scissors by gluing the knob of the solenoid to one side of the scissors and gluing the other side of the scissors to the base. By keeping the opposite side of the scissors and the frame of the solenoid stationary, we were able to open and close the scissors by pushing the cylinder in. It was easy to see the solenoid worked much more efficiently than the servo motor. The solenoid was also much stronger and was able to close the scissors with much more force and in a quicker manner than the servo motor was able to. In the circuit for the scissor mechanism, the infrared detector waits for an infrared signal. Once one is detected, the Arduino begins sending 1 pulse or digital signal per second to the MOSFET. This digital signal turns the MOSFET on, allowing the 18 volts to be applied to the solenoid. The solenoid makes the scissors close once per second. The scissors continue to open and close until the infrared detector detects another infrared signal, turning off the mechanism. The nets to gather the berries were created using traditional prototyping in order to minimize weight. There was also the need for a soft, flexible material to hold the berries in so that they would not bruise when gathered. This made rapid prototyping not ideal. We chose the location of the net in order to minimize work done by the quadcopter. We chose to put the net directly beneath the quadcopter center of gravity. The berries will become added weight to the copter, however. Ideally, the added weight would not require the gyroscope to work any more than it would when flying the original attachments. Our group proceeded with the original plan to use the quadcopter. Our initial design was to use a drone that flew similar to an insect rather than a bird and has the ability to dodge and quickly change direction or rebalance according to minor fluctuations in weight or outside forces. The quadcopter is a drone that is controlled by 4 propellers. 2 adjacent propellers move in a clockwise direction, while the other 2 propellers move in a counterclockwise direction. A gyroscope keeps the copter balanced as it moves forward, backward, up, and down. It will also keep the copter balanced if the weight of the drone shifts. This made it ideal for our project.